Greetings, everyone. Let's give people just another minute or so to join in. We certainly welcome you and thank you for being with us today. Good morning, good evening, good afternoon. We have a good attendance from all over the world. So again, let's just sit tight for a minute and we'll start shortly. Today's a very big day for IWCS. It's the deadline for abstracts for our 2025 conference. So we hope that if you haven't already, if you want to put in a last minute abstract, we would certainly appreciate that and have you join us in Pittsburgh to present your work. So again, why don't we go ahead and get started? I think, again, a few people are still joining, but again, welcome. And again, good morning in North America, but good evening, and some of you late into the evening, and also good afternoon. We welcome you to today's IWCS webinar event. My name is Dave Cadu, and I'm honored to be your CEO and director of IWCS. And I'll be your moderator for today's event. A few housekeeping items. Please note, as an attendee, you're part of a larger audience. So with that, during the presentation, all participants will be in listen-only mode. And also, this event is being recorded for rebroadcast. It'll be available on our website and on our YouTube channel if you want to share that with your colleagues or go back and watch it again. We certainly encourage you to submit questions to Bernard, our presenter today. Please use the chat function here on Teams to enter your questions by typing in the space at the bottom. And be sure to hit the send button and we'll address your questions to Bernard at the end of his presentation as time permits. So today we want to welcome Bernard Lee. He's the Senior Director of Strategic Technology and Innovation at Senco Advanced Components. He is now located in Basingstoke, United Kingdom, just outside of London. He has recently transferred from Hong Kong. And Bernard will be presenting his paper today on the connectivity advancement trends for quantum technology and its applications. And we're very honored to have awarded Bernard with the Kits Kinsley Award for the best presentation at our IWCS 2024 event in Providence last year. So we're very thankful for Bernard to join us today and present his paper again to our global audience. Bernard is the Senior Director for Senco Advanced Components Strategic Technology and Innovation Department. He is also an expert at the International Electrotechnical Commission, IEC, a chartered engineer accredited with the Engineering Council of UK. He's a professional engineer registered with the Board of Engineers in Malaysia, and also is a BICSI registered communications distribution designer, an RCDD. So again, with excellent experience, we welcome Bernard and thank you.
Right. Thank you, David. Thank you so much for inviting me. And it's a great honor to be here to present the paper again. This paper itself will very much focus on the connectivity advancement that is related to a quantum technology, and it is a joint paper between Senco Advanced Components, NPL, which is the National Physical Lab in the UK, and of course Resolute Photonics. Is a paper that we have done specifically for a application in QKD itself. So moving forward in our presentation, I'm going to first start on how applications that we have today has influenced the development of optical interconnect technologies. The last 30 years, what has happened and why, how, and when, yes, influence the technology that we have today. And of course, we look into what is quantum technology, and more specifically, the application of photonics in quantum technology for cryptography and photonic integrated systems. I'm going to touch slightly on some of the projects that we are currently doing in the UK, which is the European Horizon projects, and also the UK research and innovation projects funded by both the EU government and, of course, the UK government, and what are the current standardization efforts on quantum technology. All right, so with that, let's start with looking into the past, how application itself has historically influenced evolution of optical connectors, and now we call optical interconnects. If you want to span starting from the early 80s, a lot of the optics itself is based on long haul. It was a great system for delivering signals across a long distance. So WDM, long haul technology, very low loss fibers were mainly the focus of optical interconnect. So that's when we have the traditional connectors like FCs, SCs, and so on. So, but in the early 2000s, partly because of the internet bubble that burst in the late 1990s, in the 2000s, there were abundant of optical technology, and that gives a new application such as fiber to the home. And today, it's hard to imagine that our lives without broadband fiber connectivity to the home itself. Even a lot of governments around the world, such as Malaysia, Singapore, Australia, New Zealand, has made it a national agenda to invest and provide funding as a partnership between the government and private sector, or even totally from a government point of view, to fund fiber to the home, because they believe that fiber to the home itself will bring a growth in GDP for the whole country. But as optical interconnect provides high broadband to the homes, then there's so much content being generated. This is the growth of social media. Some of us may remember the era of Friendsters and so on, but those are a bit longer ago. Facebook, Instagram, and all of this has a place to store them. And this is where data centers start growing. Today, we have the hyperscales and, of course, the large scales of long-haul applications to interconnect all these data centers itself. So a lot of it that happens in the 2010s, 2015s, but once you have a lot of this data, you don't want to be confined to your home. The era of wireless, interestingly, has propelled a lot of the fiber interconnect technology to interconnect the base station with the towers. So you have a centralized base station. Now you have a lot of towers, more because the shorter coverage of 5G and so on, that has a lot of influence on interconnects. But going forward, after 2015, this is where the COVID struck, and that kind of accelerated a lot of our requirement for ICT technology and interconnects. That's when most recently you see the adoption of AI and so on. And those are the very key items that you see are fueling a lot of optical applications. Now, if you were to look into how it has influenced optical interconnect technology from the 2000s all the way up to what you have today, in the 1980s, 1990s, you have ST connectors, FC connectors. Those are very much developed for long haul and is being used even today in a lot of these telecom networks. Then as fiber to the home comes in, a lower cost but yet functional technology came, which is the SC connector. Coming to the data centers, because space is premium, you have the MPO connectors and of course the LC connectors that are currently being used extensively in data centers. As you go on to the outside plant, the wireless system, you have the harsh environment connectors, the IP rated ones. And with the evolution and the adoption of AI with more and more dense data centers with AI clusters, the VSFF connectors became part and parcel of today's interconnect technology. So if you look at the history itself, a lot of the applications has influenced and propelled the interconnect technology as we speak. So what is the next thing that is going to propel the interconnect technology? What's going to push us forward right now? Well, maybe it's in the field of quantum mechanics. And this is a very interesting slide that I had, photograph actually. I met Professor Michio Kaku in Hong Kong in one of the events that he had. I still remember what he says. He says, AI is the ultimate software, but quantum computer is the ultimate hardware. And the idea of having quantum computer today is maybe slightly far-fetched, but in the coming years, it will eventually become a reality because the need for it is inevitable. We will need it. It's just time when it's going to come. But if you dive deeper into quantum technology, quantum mechanics itself, quantum mechanics or quantum technology is kind of divided in three different main sectors. One, as we see a lot of the quantum chips that are being announced recently, is in the field of quantum computer, doing processing with quantum itself. The other one is quantum sensing, highly sensitive, highly accurate sensing technology that we use to sense gas, temperature, even biochemical changes. And of course, what we're going to focus today itself for interconnect is the field of quantum communication, more specifically, how to secure quantum information across space, or quantum cryptography. Okay, so what do we need in quantum cryptography? What kind of interconnects do we need? Well, one of the reasons why we need it is that in future, hyperscale technology will need quantum computing, because in a way right now, quantum computers will be the center of a lot of the processing, but around it, it needs the security, the artificial intelligence in terms of software, and of course, the quantum communication to provide a secure link. Quantum cryptography, or in this case, quantum communication, requires a technology called quantum key distribution. So quantum key distribution currently is being used in multiple different places to ensure a secure link between the sender and the receiver. But how does it actually work? It's a very key question here. So if we look at a normal link right now, you have Alice, who is the usual name for the sender, from A to B, Bob, commonly used as the name for the receiver. And in a normal optical channel, you send photons in terms of optical signal across from Alice to Bob. Okay. And Bob receives it, decodes it. Hey, I got the signal. Perfect. But in an insecure system, you have Eve, who is an eavesdropper or hacker that will be trying to get the information from this link. So as Alice sends this information to Bob, Alice is going to tap into it. And then from there, she'll be able to get the information that is to be shared. Bob has no idea that he has been tapped, and the link itself is insecure. Eve goes away with the required information. Of course, in a normal optical channel, that is not that easy, because what you do in a normal optical signal is that you have the data encrypted, and only Bob, who has the decryptor or the key to decrypt the data, will be able to read the data itself. Eve, although she gets the data, is of no use to her. But what if Eve has also the key? When Alice sends the key to Bob, Eve gets a copy of it, and then she'll be able to decrypt anything that is sent from Alice to Bob itself. Highly insecure, although this is how it works today in all of our communication. Now, coming to a quantum channel, instead of sending a bunch of photons, Alice sends one entangled photon to Bob. Bob will observe the photon and read the quantum state, and that is where the information is sent from Alice to Bob, and only Bob can read it. If Eve tries to steal the photon that's coming from Alice to Bob, let's say she's going to read it, but once you read the photon itself, the waveform collapses. So even if she makes an exact copy of the photon and send it to Bob, Bob will know, hey, something's wrong. Someone has read the photon. This system is insecure. So this is called a no cloning effect. And this uses a property of quantum, which is the superposition, or where the angle of the qubit will be, and of course, quantum entanglement of both the photons, that is Alice and Bob itself. Of course, this is not the way you send information. What you use quantum key distribution for is to just send the key to the information. If you look at a QKD system that is right now being deployed around the world, the QKD module will send the key over the QKD link using the same fiber, but the data itself will go on a standard conventional link using regular modulation and coding. So once the key is over, everything's secure, data can flow. As long as the QKD key is fine, the data itself is secure. And this you have seen being used and deployed by various telcos for high-speed secure communication in terms of metro and trunk networks, and even long haul using satellite QKD systems. So the question here that we were given by the network operators is, what kind of connector or what kind of requirements do we need for a optical link to handle QKD? So in reality, what will happen is that from Alice to Bob, this is a physical fiber. And this fiber can go from 20 to 30 kilometers across. Itself will have different interconnects in between, now usually splicing. But what if we have a connector? And a connector is not in a good, doesn't have a good performance that you'll create a certain loss or even make the waveform itself collapse. So what do we need is, of course, a quantum repeater. It's still in work in progress. But at the same time, we have ultra low loss component, passive components like connectors, maybe even splitters, and of course, fiber itself. Because remember, the power of a photon is about minus 100 dBm. And that is the amount that will go from Alice to Bob. Every single dB loss is very important. Right. So how we're going to focus mainly on the ultra low loss interconnect, which is the connector. So what would be the real spec for a ultra low loss internet connector? First of all, we are looking into what causes losses in an optical connector. The insertion loss and return loss of connector is provided by different effects. If you look at the equation here, anything that is being sent over will have alignment, and of course angular, and of course the polishing of the end face of the connector will provide the return loss. So the number one thing that we want to do is to make sure the alignment of the fiber. Again, connectors are just holders of fibers. So if we have the connector being aligned properly in the lateral offset and also in the angular offset, we should get a almost perfect, if it's everything is in a line, interconnect. So how do we do and how do we ensure a good interconnect alignment? Well, if you look at the whole process of how a connector is made, first thing we need to do is to find the right material. This is governed by various different international standards like in IEC and TIA. And of course, the other one is like in the manufacturing, how the connector is being manufactured to ensure the highest quality. And in terms of material, you have the two key important things is the ferro and the fiber. And in manufacturing, repolishing, and of course, how to attach the fiber to the ferro, which includes the epoxies and so on, the curing process. And there's a whole load of things that is attributing to it. Now, if you look at the material point of view, the ferro itself is never circular. So ideal ferro, which is in A, and a fiber and ferro itself, is having the core and the cladding specifically right in the middle. But that does not happen because they're always offset of the core in B, and C and D is the shape of the core. It may be elliptical for both the core and of course the cladding itself. And all this has an effect on the lateral alignment. Now, after we got the best fiber, what kind of ferro we want to use? So you put the fiber into the ferro. Is the ferro too big, too small? Is it at the right center, and so on? So the concentricity of the fiber and the tolerance of the fiber hole in the ferro will be very key. So once we look into the fiber, we select the right one. Now we have to select the ferro itself. Once we do that, we want to look into, sorry about that. We want to look into the manufacturing of it. So once the fiber is put into the ferro, it needs to be polished at the right angle. And of course, the fiber in the ferro has to be at the right position to give a physical contact. At the same time, because we know that the fiber and the ferrules are now perfect, you may want to do some kind of angular tuning to make sure that the fiber core is right in the middle of the connector itself. Now, as we know, the material and of course the manufacturing itself is important. What kind of standard is out there, or what are the targets that we should be looking at in making a connector for QKD application? Unfortunately, there's no. So our counterpart came back and told us, hey, can you make an interconnect connector as good as a splice? Challenging, but we took the challenge and say, okay, what is the international standard for a splice? Back in ITU, you have the insertion loss of a splice would have to be 0.1 dB, less than that. And the return loss will have to be higher than 60 dB. We took that, and this is the same requirement of a fusion splice. We make our connector based on the best fiber and ferro that we get and control our manufacturing process. We stuck it into the testing for a back reflector meter. To our surprise, most of it are less than 0.05 dB, both in terms, in insertion loss, both in 1310 nanometer and 1550. In back reflection, we were doing an extra step in terms of the polishing. We are easily getting above 80 dB in terms of return loss. So again, the numbers are very impressive, but is it real? What we've done later on is to stick the connectors into a length of fiber, and we shoot a OTDR into it. And in order to make sure that we do not degrade the end face of the connector, we use a gel cleaner instead of a regular white type. And to our surprise, we were unable to detect the connector in the OTDR. This is what we got on the screen from the OTDR. This is the end face. Sorry, this is the trace of the OTDR itself. This location circle in red is supposed to be where the connector is. On the OTDR, it was no events. There was no event being recorded. That is the location of the we call it the QPC connector. Then what we did is that, okay, we've done the component testing, we've done a link test. The next, what we've done is to work with MPL, and MPL put it into their testing methodology and confirm that yes, the insertion loss that we achieved were less than, majority of it less than 0.05 dB. And we had a press release, and this was the basis of a quantum performance connector that is being used today, even in MPL labs right now. So that was part of the optical connectors for QKD. But QKD is one part of the link. How about connecting the PIC right now, which is a photonic integrated circuit for QKD application, directly from the board outside to the outside world? So the quantum interconnect for QPIC became a key research for us. So what is the efficiency of using on-board optics or CPO co-packaged optics? Right now, of course, we have the pluggable optics right at the front of the switch. As we bring the fiber deeper into this equipment itself, we need an interconnect to the board. And this was NPO, near package optics. But we are trying to go all the way down to the packaging of the PIC itself, and we call it co-packaged optics. And one of the advantages of this is that we can reduce the amount of power consumption all the way down to 5 picojoule per bit. Now, how do we attach the fiber to the PIC, which may be used for the QKD's random number generators? We can use a very conventional way of having a fiber and then a reflector onto the PIC. This is very common. This has been used in many years for silicon photonic application. What we are proposing, instead of using what you see here, even if we can do a curve polishing at the end, there is the problem of height. And of course, because this is all packaged, and the control of the angle itself is less. Another way of doing it is to have the fiber bend 90 degrees. This is even thicker than what we saw just now. And this itself has a higher loss in terms of the angle of the light going into the PIC and coming out of it, unless you have a lens before that to put in. One of the technologies that we are trying here, and this is part of a UK research program, is to have a mirror being, see, here's a pointer. This is a metallic mirror that can be shaped to any focal length within tolerance specs. And as the light goes from the PIC into the fiber, it can be refocused to the specific area of the PIC or even the fiber core itself. So, and the same mirror can be used for in and out onto the fiber and the PIC. But also, it can be used as a meatball interconnections between fiber to fiber. Again, this is being used because the curvature of the mirrors can be tuned to minimize the loss as it transmits it. Now, another advantage of this is that as we want to test the system, we can detach the connectors so that we can scan, we can do a cleaning, or even there's a faulty part, we don't want to throw away the quantum PIC itself, we can be able to just take away the fiber and put in a new one. All right, so these are different interconnects that is suitable for extreme low loss to a quantum PIC or even the interconnect between a quantum link. Next is the advanced projects that we have done in terms of the funding from the UKRI. This is one project called QPICs. It's a packaging technology whereby we were able to connect the fiber to the PIC. And this is a collaboration between Wave Photonics, Alta, Senko, Bristol University, Southampton, and of course, the whole effort is being funded by Innovate UK. So we have packaged the QPIC onto a gold box packaging. We've put it into the packaging itself and then tested it with different wavelengths. The key advantage of this is that it is a grating method that can cover the whole C-band. So we're trying to find a interconnect system that is able to not focus on specific wavelength, but more of a broader wavelength itself. Again, thanks to MPL, we have sent it to them for metrology, and from what we have seen itself, the insertion loss has been about 2 dB for a interconnect from the fiber to the chip. This is minus out the MPO connectors and the loop back link itself. Right, and again, this effort is being funded by UKRI. So the other project that's ongoing right now is a partnership between Seagate, Senko, Resolute, Wave Photonics, and MPL with the chip from Cornerstone, whereby we're doing the next generation of a package QPIC itself for a H coupling. So now we did previously with QPIC on a grating coupling, now we're doing an H coupling method. And all this is being a step nearer to having what we call quantum as a service. All right. So hopefully all this technology itself is going to help us to move nearer to have quantum as a service to the greater public. Right. So the conclusion for the time being, what's going to happen is there's a lot of effort being put into here for the effort of standardization. So ISO, ITU, IEEE, Senelec, ETSI, and IEC all has efforts right now trying to standardize quantum components for QKD applications. Most recently, just yesterday, there was a kickoff in IEC called Working Group 11, where they're going to start drafting interconnect standards for quantum connectors. And is going to go beyond that in the future, of course. And if there's anybody who would like to know a bit more about this, please feel free to contact me. I'll be happy to link you to the right working group. All right. So in conclusion, hopefully just in time, we have reported a development in how to characterize ultra low loss quantum grade interconnects. And we have done it both for links and of course fiber to the chip. There's a lot of research being done right now to further extend this technology. But at the same time, standardization is coming in to make sure that we have a standard performance for quantum key distribution application. Now, is this the end? Well, we're not sure. And that goes to my last slide. And hopefully, if anybody's interested on this work, please contact me, and we'll be more than happy to see how far the rabbit hole goes. With that, thank you very much.
Bernard, absolutely fascinating, and we thank you for bringing together such a complex topic, or just the theory being transferred into practicality is really what's so exciting. And of course, in our space, we're trying to determine what's the infrastructure to move those packets of data, those photons and those repeaters. And I guess the first question for you is, what is the next step in terms of the evolution of technology to move photons and again, the repeater technology to move across campus and then ultimately across communities, and cities and even more broadly? What's the next step that you need from our industry?
Well, again, if you look at QKD application, the work for a quantum repeater is still ongoing. It is something that the amplifier technology has to be ready, but how much will it influence the qubit is a big question. On the other hand, from a passive infrastructure itself, we're trying to lower the insertion loss as far as possible. Here, we are focusing on connectors. The other one is a new advancement in ultra low loss fiber.
Right.
So from what we know previously, fibers has a 0.25 dB per kilometer in 1550. There are long haul fibers at less than 0.2. And now, if you look at OFC recently, the advancement in hollow fiber is astonishing. They are claiming 0.1 dB per kilometer right now. Hollow fiber is not a widely available technology, but it's moving towards. But if it does have the promise of a lower loss with a longer link, that may justify the cost that is being put into investing in hollow fiber links.
Good. Clearly, you know, the work that needs to be done is a collaborative effort, you know, between university that you referenced in the UK and some of the alliances, both, you know, with government and the private sector. And actually, we're very excited in IWCS to be focusing on this technology as well and working with the entities down in Richardson, Texas, which is there's a lot of coordination being done to actually generate a quantum communications test bed. And again, a collaboration between quantum computing hardware companies, the National Security and Innovation Council, the Texas Research Alliance. So between what's going on in the UK and what's going on here in the United States, how can we bring our community, our companies together to contribute to this effort? Because still a lot of learning that needs to be done in order to generate the infrastructure that we're going to need. And again, I'll shamelessly promote this for IWCS 2026, 2025 and 2026 in Pittsburgh this year and next year in Orlando, to really bring companies and bring people together to try and get to this point. But how do you see these alliances coming together to bring about this technology evolution?
Oh, the first interaction that we had on a global alliance or global collaboration on quantum was first done by ITU on a focus group on ICT for quantum networks. Very loosely, a lot of volunteers in there, and we were sharing different case studies, different technology that will promote the application of a quantum link, both for wireless and of course wired version. That was the first one. That was if you look at ITU itself, there's a report being published. But more concretely, right now, and actually just yesterday, the kickoff meeting in IEC. So IEC, the international body for electromechanical technology, they have started a working group on defining what is required to enable a quantum link. Again, that is currently led by the UK as the secretariat, but it is an international body. It is kind of an ISO, IEC collaboration, so it's international. Richard Pitman, who is the chair of it, is the CEO of Resolute Photonics. If anybody's interested to get a bit more information or contribute to this standard, please feel free to contact me. I'll put you through to Richard. And we hope more participants to offer and share what their technology, which can be part of the standards moving forward.
Yeah. Well, IWCS will work hard to help bring those entities together, whether it be in codes and standards, whether it be in manufacturers of fiber, connectors. We want to bring everyone together, and we'll be working on that as part of our conference program in Pittsburgh in October. Question is, we've seen the use of multi-core fiber for QKD. Can you speak to the advantages of using those types of fibers?
Well, multi-core fiber is part of the densification called space division multiplexing. So again, there's a modal SDM, and of course, having multi-core fiber is also a part of SDM itself. One of the key advantages of multi-core fiber is that in PICs, the spacing of the waveguides in the PICs are very narrow. In order to couple this waveguides, the signal from the waveguides into fiber, which is a lot larger, it has to be spread out. So if we use multi-core fiber, we can still maintain the density of all these waveguides to the pitch in the core itself. So imagine your waveguide in a PIC is usually 3 nanometer. 3 micron. And then the core of a fiber is 9 micron, single mode, but the cladding is 125. So you have no choice to space your waveguide so far apart. But if you have a denser multi-core fiber, you do not need to space them. So you have a shoreline density advantage. So in this case, you can have a smaller, more dense coupling from fiber into the chip itself. Nevertheless, now once you get the signal out of the fiber, into the fiber, how do we split the signal? Do we maintain the 4-core, for example, or do we separate the 4 cores into 4 different directions? So again, those splitting of the core will induce loss, which may not be favorable right now for QKD applications.
In the conventional technologies, I say conventional, the current technologies of data transfer, it's about the data being sent, verifying that the data was received, and so it's like it's a back and forth, very fast, obviously, communications between the sender and the receiver to verify that the correct data has arrived. Do you see that in this new technology for quantum communications and technology, is this type of verification happening in each repeater, basically as we get farther and farther away from the source, to maintain the integrity of the photon, remain the integrity of the packets of data? Is that where you see this change in the technology?
Well, until we have a quantum repeater, the length of the link itself is determined by how much insertion loss we have in the link before the signal becomes unreadable. So what we call a quantum hop itself, from the sender to the first bulb, it has to be decoded, get the key through the QKD, get the data, and then recode and send it off again, or again regenerate the key and move on, would have to be the only option that we have. Most of the commercial QKD systems are a single link, maybe just one hop, and these are usually secure links between two ends of a communication link. Hopefully that answered that question.
Yeah. No, it's fascinating to rethink how we're looking at the transfer of data, from where we were to where we want to go, and the technology that has to be developed to make that happen. And I think that's what our unique audience here that's involved in that infrastructure is going to have to figure that out. But I do want to mention that there's a lot of work going on. You mentioned in the UK, and again here we're trying to create in Richardson, Texas, a sort of quantum communications corridor, if you will, as I've heard it referred to as the next Silicon Valley for this space anyway, and is exciting, and we'll be again talking more about that within our program, and hopefully bring companies and technologies together to make that happen. I don't see any more questions. So with that, I want to again can't thank Bernard enough for his time to be with us today and to present his work.
Thank you.
And as Bernard mentioned, if you want to reach out to him directly, you can see on your screen his email address. And again, we're very fortunate that we'll be elaborating this technology. Bernard will be back with us in Pittsburgh. He has submitted a couple more abstracts to continue this conversation. Again, we thank him for that contribution. Our IWCS webinar series event happens each month. And our next technology event will be in May. It's typically the third Friday in each month. And the next one will be Friday, May 16th, 10:30 in the morning, USA Eastern Time. We're looking forward to another great presentation from CommScope. It's important that we recognize. I did the slide here. I do want to mention today has been a very special day for IWCS. Today is the official deadline for submitting abstracts for the 2026 conference. So again, if you have any contributions you wish to make to our program and share your incredible innovations to our global audience at IWCS, please submit your abstracts. Very easy to do. Again, if you have any late minute work, please feel free to reach out to us and submit those topics. But today is the deadlines, and we look forward to reviewing those next week and establishing the program together. But again, as I was going to mention, we must recognize our partner level sponsors and thank them for greatly contributing to the success of IWCS and our Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important innovations and technologies to you and our global audience. And so again, we thank these leading suppliers, and we look forward to having each one of them part of the discussion again in Pittsburgh in October. So please save these dates. Again, as Bernard was elaborating on some of these things, it's a very, very active opportunity in this particular conversation of quantum communications and quantum computing, AI, and we'll be focusing on that technology in Pittsburgh. So make note of the dates. We hope you will join us there. Again, please take a look at our website to learn more. The dates are Monday through Thursday, October 27th through 30th. And we'll be describing a lot more about what's going on through social media channels and also eBlast communications. So feel free to share that with your colleagues. And with that, I want to thank you all. You have a great weekend and look forward to seeing you again shortly next month. Take care.
Thank you.
Thanks, Bernard.